To convert metric wire sizes in square millimeters to American wire gauge and kcmil, it's essential to have a conversion table. The table provides a direct mapping between the metric size, the equivalent AWG size, and the corresponding kcmil value. The table includes the following conversions. 150 square millimeters corresponds to 0 AWG, which is equivalent to 500 kcmil. 185 square millimeters corresponds to 0 AWG, which is equivalent to 750 kcmil. 240 square millimeters corresponds to 0 AWG, which is equivalent to 1000 kcmil. These conversions are vital for selecting the correct wire size in electrical installations, ensuring that the wire can safely handle the intended current load. When working with electrical systems, using the appropriate wire size is critical for safety and performance. Undersized wires can overheat, leading to insulation damage, fire hazards, and voltage drops that can impair the operation of connected equipment. Oversized wires, on the other hand, can be unnecessarily expensive and difficult to work with, especially in tight spaces. Therefore, precise conversions between metric and American wire sizes are essential for designing and installing electrical systems that meet safety standards and functional requirements. Firstly, consider the application. Different applications have different requirements for wire size. For example, a high current application, such as powering a large motor or supplying an entire building, will require a larger wire size than a low current application, such as lighting or powering small electronic devices. Secondly, determine the current carrying capacity. The current carrying capacity of a wire, also known as its ampacity, is the maximum amount of current that the wire can safely handle without overheating. The ampacity of a wire depends on several factors, including its size, material, insulation type, and installation conditions. Thirdly, select the appropriate wire size. Once you know the required ampacity, you can select the appropriate wire size from a wire size chart. Wire size charts are available in electrical codes and standards. They provide the ampacity of different wire sizes for various insulation types and installation conditions. The National Electrical Code, or NEC, provides tables for determining the allowable ampacities of conductors. These tables take into account factors such as the conductor material, insulation type, and ambient temperature. For example, NEC Table 310.15b16 lists the allowable ampacities of insulated conductors rated up to 600 volts, based on the conductor temperature rating and the ambient temperature. When using these tables, it's important to apply any applicable correction factors for ambient temperature or the number of conductors in a raceway or cable. These correction factors reduce the allowable ampacity to account for the increased heat generated when conductors are grouped together or when the ambient temperature is high. kcmil stands for thousands of circular mils. A circular mil is a unit of area used to describe the cross-sectional area of a wire. 1 circular mil is the area of a circle with a diameter of 0.1 inches. kcmil is often used for larger wire sizes because it provides a more manageable number than circular mils. For example, a 500 kcmil wire has a cross-sectional area of 500,000 circular mils. To convert from square millimeters to kcmil, you can use the following formula: kcmil equals square millimeters divided by 0.5067. To convert from kcmil to square millimeters, you can use the following formula: square millimeters equals kcmil multiplied by 0.5067. These formulas are based on the relationship between inches and millimeters and the definition of a circular mil. However, it's generally easier to use a conversion table or an online calculator to perform these conversions, as these tools eliminate the need for manual calculations. When selecting a wire size, it's important to consider not only the ampacity requirements but also the voltage drop. Voltage drop is the decrease in voltage that occurs along the length of a wire due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. To calculate voltage drop, you can use the following formula: voltage drop equals current multiplied by resistance multiplied by length. The resistance of a wire depends on its material, size, and temperature. Wire manufacturers typically provide resistance values for their product. To minimize voltage drop, you can use larger wires or shorter wire runs. In summary, converting metric wire sizes to AWG and kcmil requires careful consideration of ampacity, voltage drop, and installation conditions. Using the correct wire size is essential for ensuring the safety and performance of electrical systems. The provided conversion table offers a quick reference for converting between these different wire size systems. The relationship between metric wire sizes, AWG, and kcmil is based on the cross-sectional area of the conductor. The larger the cross-sectional area, the more current the conductor can safely carry. AWG is a logarithmic scale, meaning that each decrease in gauge number represents an increase in wire size. For example, a 10 AWG wire is larger than a 12 AWG wire and can carry more current. The NEC specifies the allowable ampacities for different wire sizes and insulation types. These ampacities are based on the assumption that the wires are installed in a manner that allows for adequate heat dissipation. If wires are bundled together or installed in a hot environment, their ampacity must be derated to prevent overheating. When working with electrical systems, it's always best to consult with a qualified electrician or engineer to ensure that the wiring is safe and compliant with all applicable codes and standards. Selecting the appropriate wire size involves a balance of factors, including cost, performance, and safety. While larger wires can carry more current and reduce voltage drop, they are also more expensive and difficult to install. Therefore, it's important to carefully consider the specific requirements of the application when selecting a wire size. Furthermore, it's essential to use the correct tools and techniques when working with electrical wires. This includes using properly insulated tools, making secure connections, and following all safety precautions. Electrical work can be dangerous, and it's important to take all necessary steps to protect yourself and others from harm. Finally, remember that electrical codes and standards are constantly evolving, so it's important to stay up to date on the latest requirements. This can involve attending training courses, reading industry publications, and consulting with experts in the field. By staying informed and following best practices, you can ensure that your electrical work is safe, reliable, and compliant with all applicable regulations. When dealing with electrical systems, understanding the different types of conductors is also crucial. Conductors are typically made of copper or aluminum, each with its own advantages and disadvantages. Copper has higher conductivity than aluminum, meaning that it can carry more current for a given size. However, aluminum is lighter and less expensive than copper, making it a popular choice for large-scale applications such as overhead power lines. The choice between copper and aluminum depends on factors such as cost, weight, and performance requirements. Another important consideration is the insulation type. The insulation surrounding a wire protects it from damage and prevents electrical shock. Different insulation types have different temperature ratings and resistance to moisture, chemicals, and abrasion. The NEC specifies the appropriate insulation types for various applications. For example, THHN insulation is commonly used for general-purpose wiring in dry locations, while THWN insulation is suitable for wet locations. In addition to wire size and insulation type, the method of installation also affects the ampacity of a conductor. Wires can be installed in various ways, such as in conduit, cable trays, or direct burial. Each installation method has its own thermal characteristics, which can affect the ability of the wire to dissipate heat. The NEC provides guidelines for derating the ampacity of conductors based on the installation method. When installing wires, it's important to follow these guidelines to ensure that the wires do not overheat. Proper grounding is another essential aspect of electrical safety. Grounding provides a low resistance path for fault current to flow back to the source, which helps to protect people and equipment from electrical shock. The NEC specifies the requirements for grounding electrical systems. These requirements include the use of grounding electrodes, grounding conductors, and bonding jumpers. By following these requirements, you can ensure that your electrical system is properly grounded. Furthermore, surge protection is important to protect sensitive electronic equipment from voltage spikes caused by lightning strikes or power surges. Surge protective devices, or SPDs, are designed to divert excess voltage to ground, preventing it from damaging equipment. SPD are available in various types and sizes and should be selected based on the specific needs of the application. It is important to consider the short circuit current rating, or SCCR, of electrical equipment. The SCCR is the maximum amount of fault current that the equipment can safely withstand without causing damage or creating a hazard. Electrical systems must be designed to ensure that the available fault current does not exceed the SCCR of any equipment in the system. This can be achieved by using current-limiting devices, such as fuses or circuit breakers. Another important aspect of electrical safety is arc flash protection. Arc flash is a dangerous phenomenon that can occur when a high-voltage electrical fault creates a sudden release of energy in the form of heat and light. Arc flash can cause serious burns, injuries, and even death. To protect workers from arc flash hazards, it is important to perform arc flash hazard assessments and implement appropriate safety measures, such as wearing personal protective equipment, or PPE, and using arc flash rated equipment. Electrical systems should be inspected and maintained regularly to ensure that they are operating safely and reliably. Regular inspections can help to identify potential problems before they lead to failures or hazards. Maintenance activities such as tightening connections, cleaning equipment, and testing devices can help to prolong the life of electrical systems and prevent costly repairs. In addition to the technical aspects of electrical work, it's also important to be aware of the legal and regulatory requirements. Electrical work is regulated by various codes and standards such as the NEC, which are adopted and enforced by local jurisdictions. It is important to comply with all applicable codes and standards to ensure that your electrical work is safe and legal. When planning an electrical project, it's important to obtain the necessary permits and approvals from the local authorities. This may involve submitting plans, undergoing inspections, and paying fees. Failure to obtain the necessary permits and approvals can result in fines, delays, and even legal action. In conclusion, electrical work is a complex and challenging field that requires a combination of technical knowledge, practical skills, and attention to detail. By understanding the fundamentals of electrical theory, following best practices, and complying with all applicable codes and standards, you can ensure that your electrical work is safe, reliable, and compliant.